Electrostatic, topic 12. We are now the last section, 12.4, electric potential. Right? We are now 12.4, that's your syllabus. We need to define, know to use this formula, and then explain the meaning of equipotential surface.
Okay.
Use this relationship, and then this relationship also, which is your potential energy or work done. Okay, so I expected you to do all these questions. In fact, you should try all the focus question already, not all these questions alone. The section B and section C, not A alone.
Oh, okay.
Right? Remember that electric field strength is a vector. So wherever we add vectors, we have to use either parallelogram rule or triangle rule or polygon rule, and it becomes very complex. Difficult to calculate, a lot of work involved. When describing a field, potential is usually more useful quantity than electric field strength. Why? Because it's a scalar. Scalar, you just add or subtract only, and can be added directly when more than one field is concerned. You can have different charges contributing to the field. So if you use electric field strength, there are so many vectors for you to analyze. Like the potential, you will see where just add or subtract only. So
Because the other one, because electric field got direction and it's like complicated. That one is
the
like more
direction, you
simpler.
have to
That's
be
why.
aware of the direction. No? Whereas electric
Yeah,
potential, don't need to worry about direction.
because straightforward lah, scalar only. What you need the
Straightforward,
charge
either
and
positive or negative value. You have to remember. That potential
okay.
is the work done per unit charge in bringing positive charge from infinity to the point. So we bring 1 coulomb of charge from infinity to the point.
To the point.
If you are interested in the potential at the point.
So basically, bringing 1 unit of positive charge from infinity to a point. That's it, right?
Yes. Just the work done divided by the charge you have taken. Right? Or we call it test charge. That's the charge that you take. Potential at infinity is 0. Right? We choose that easier because the force at infinity is also 0. It's a scalar quantity. Unit is volt or joule per coulomb. Right? Joule per coulomb. Right? Remember, if it's a positive charge, usually we take a positive charge. There's a repulsive force there to bring the charge from infinity to the point. Right? There's a repulsive force there. So basically, if there's a repulsive force, it means that if I have a positive charge, I want to find the potential of this positive charge. I have to bring a test charge there, Q, from infinity to the point. So it's going to be a repulsive force. So a repulsive force means I have to do the work. The external agent has to do the work. And this work is stored as potential energy. So when you let go, then the charge will go to infinity, where the potential energy is 0. Okay. So
Just a minute, sir. For the potential of a positive charge, work has to be done to bring. Okay, and the force is repulsive. Can you explain again? I don't understand what is it trying to tell.
basically, you have a positive charge, big Q. You have to take another positive charge from infinity. So the force is repulsive. The force is repulsive. So it means I have to do the work, not the field. I have to do the work to bring the charge from infinity to the point there.
Both
so
of it are.
The energy is stored as electric potential energy. So if I let go, then the charge will shoot off to infinity. That's what I mean.
No, I mean both charges lah, right? Sure.
Usually we consider the big Q as stationary lah.
No, what I'm trying to ask is because you say you have to you have I mean you have to do the work done, right? So not the force,
I
right?
have to do
So,
the work done.
but then like are we moving the two charges or only one? That's what
Only
my
one charge only.
question.
One charge is stationary. It's not moving.
So that one no need to bother lah.
You just memorize the definition, that's all. Definition doesn't say
Okay, no,
any. Just move a
no,
test
I'm
charge
just trying
only.
to understand only.
Definition doesn't say any charge. Right? It just move a test charge, that's all. That's all you need to remember. Don't read
Move
too
for
much
test
into that.
charge.
Then after that, we want to calculate.
Oh, okay.
We are just assuming the field is contributed by a positive charge as well. Okay, unit is joule per coulomb, or we call it volt. Okay, or W we call it potential energy. Either work done or potential energy is the same thing. So now we want to calculate the potential due to this positive charge at a point P, a distance R away from this charge there. This is the charge that contributes to the potential. So you want to calculate the charge due to this, the potential due to this charge at a distance R away. There's a point there, point P, and that's a distance R away. You want to find the potential of this charge there, this Q, at this point P, a distance R away. Okay, and that is the formula we are going to derive. And this dark line is the electric field strength, E. It's always coming out straight line from the positive charge. Right? So another way of thinking of potential is potential energy per unit charge. So potential energy is basically just our V times your Q. Right? That's your definition for your potential, your volt or potential difference. Okay, so that formula you must remember. This formula you must remember and know how to use it. But how do we derive it? Right? We go to a definition. Right? We are interested in this is a charge that contribute to the field. So we are interested to find the potential at P, a distance R away. So we are going to move a test charge, right? That small charge that Q at infinity to the point P. Right? So we are just now using the definition, that's all. Right? So the force between this charge and this charge is given by Coulomb's law, F. Right? That's why we define from infinity to the point. Right? The force is going outwards. The small distance is going to the left. So the two are in opposite direction. That's why we put a negative sign there. And then we integrate from infinity to R. Memory will only nothing much. Now to derive it. Then replace that force there with this formula, Coulomb's law. Yep. And then we just integrate it. Right? Integrate that. There's a negative from here, becomes positive. Then we put in your value. Okay. Infinity is 0. So we only got QQ 4 pi epsilon naught R. Then we use our definition for potential difference. W divided by Q. So that is why we calculate W or U divided by our test charge. This is your test charge, remember? Then we get our formula. Yep. Any problem?
Wait, okay, we do that calculation and then F and then so why dx going to the left, huh?
We are moving for infinity, infinity to the left, Yeah, we are taking the charge from infinity downwards to P. That's why it's to the left. Okay, now displacement and force are in opposite direction.
Displacement. Oh, so the force is the displacement and the dx is like opposite lah.
Dx is the displacement, F is the force. So both of them are in different direction. So that's why we have to put a negative sign there to show that the two are not in the same direction.
I still don't understand, lecture.
This is basic physics. Force in one direction, displacement in opposite
Okay.
direction, then it must have a negative sign there. If the force
Wait, dx is displacement,
dx is displacement, a small displacement.
Oh, okay. Then sorry, then I thought it was something else. Sorry.
Okay. The next, we are just using the formula, that's all.
Sure, but the kqq over x square, right? Sure, when you put inside the equation, where's the other x?
Integrate it becomes this minus 2 plus 1 is becomes 1. No?
Okay. So that's integration. Oh, okay. I forgot that. Okay. I didn't know you integrated that.
Okay.
Okay, charge over. Oh, then you times Sunila with the R and everything. Oh yeah, K is 1 over 4 pi r epsilon naught. That's why you substituted inside. So that's why, and then you substitute the x with R and then minus with the infinity. Yeah, that's why you get that lah. Yeah, okay.
Okay, let's go to the next slide. Okay. So in our derivation, we first of all have to calculate the potential at a point. We first calculate the work done in moving the positive charge Q from infinity to the point. Right? That's what we are doing. If you want to convert it, you can convert it from negative to positive. You want to. So what are we doing? We are actually calculating the shaded area. That's all. If it's for the separation graph, right, where this separation is your x. Okay, so we won't bother about that. Okay, so how does the graph looks like? Charge conducting sphere or radius r. The radius of the conducting sphere is r. The charge on the sphere is q. Remember, we said the charge is on the surface of the sphere. Inside there is 0, no electric field. Right? Charge reside on the surface because that is where they can be as far as possible from each other. They will repel each other. Right? So the sphere is an equal potential volume. That means the potential anywhere is a constant. Right? Given by this value, potential is constant inside the sphere, on the surface of the sphere, all constant, given by this formula. Right? That's why it's a horizontal line there.
Tell again, sir.
The sphere is an equal potential volume. That means within the
Okay.
sphere or on the surface of the sphere, the value of potential
Same
is
charge.
this value. That's why when we draw the graph of potential against separation, it's a horizontal line. So it's a constant.
I mean the same charge lah, right? Sure.
Yeah, same charge. We think the charge
Okay.
as if it's behaving at the center. But outside the sphere, where the separation r is greater than the radius of the sphere, then it's follow this formula. Right? That means inversely proportional to r. As you go further and further away, it becomes smaller and smaller. That's what it means.
Wait, the left one is also inversely proportional also, right? But increasing.
Yeah, same thing. Don't worry about the left hand side. It's the same as the right hand side.
Just memorize it only lah.
Yeah, remember the graph.
Okay.
So sometimes they may ask you to sketch accurately. Right? If they give you the value at the surface is V naught, then you must remember the formula, the formula. Then know that your V times R is a constant. Right? So that constant can be obtained if it's on the surface of the sphere, it's just V naught times R, that's all. Then you can count and calculate what happens if it's 2R. Right? So V is just V naught R take the R down, get that, then put your value of R inside there, 2R, you just divide by 2, 3R divide by 3, 4R divide by 4. Right? If they give you a proper graph paper, ask you to sketch properly, then you have to calculate. That's your table. Right? So at R, 2R, 3R, R is, remember, is the radius of the sphere. So at the surface there, V naught. Then after that, half of it is here. 2R is half of it is here.
That means they keep
3R,
decreasing as the distance increase.
Quanta is about here. And a quarter is about here.
So potential decreases as the radius increases. Right.
Right? At the surface here is constant. If they give you a graph paper, ask you to sketch accurately, then that's how you do it. Okay.
Okay.
Electric potential G is defined as the work done to bring the positive charge from infinity to the point. So infinity at a point is V, then the electric potential U at a point is just your U times V. And the potential we have calculated there is Q 4 pi epsilon naught R. So at the surface, there's a value. Potential here at the surface of the sphere. Okay with that? This at the surface only. Right? If you want to outside the surface, then you have to replace the big R with small r. Right? Your page 19. Okay? Okay or not? Okay, let's try some example. We can try this one out. Basically, just using this formula to give you experience how to calculate it.
Okay. Triangle ABC is a right angle triangle with angle C at 90 degrees Celsius. AC is 8, AB is 10, means find the potential at B due to the charge at A. So we take the charge at A, negative 4 times 10 to the power negative 9 over 4 times pi times epsilon times since they put there AB 10, so 0.1 0.1 square lah. Is the calculation correct?
What is the answer?
Wait, answer. Give me a minute. Let me calculate it. I got wait, what? I got 3,600.
Something is wrong already.
Teacher, but then the radius isn't it supposed to be square?
No, square. Square is a electric field.
Yeah, actually, right. I did the thing correctly, but then the problem was I kind of
Use
put
the
the
wrong
radius
formula.
square.
No square, no square.
Yeah. Oh, okay, careless. Sorry. Oh, that means radius. No, this one lah. Okay.
Radius no square.
I remember. No R square for electric potential. Okay.
So you get
Only R, right?
minus 360 volt.
Yep. Sorry, my bad. I didn't notice the R square. Okay, I tried the other one. Where's the question?
Potential at B due to a charge at C.
Wait, Archer. Potential at B due to the charge at C. Okay, so we don't know the B, this one, so we take the C one, so plus 5. 5 times 10 to the power of -9 divide with 4 pi epsilon 0.06. There's no square here, so 1 minute, sir. Uh, 749.
Okay.
I got 748.96 lah, so yeah.
Then the next one, what's the answer?
What's the question?
Potential
Okay.
at B due to both charges. How to find the answer?
Oh, campur ni lah, teacher.
Yeah, campur ni.
Oh, teacher, I wanted to ask before campur, right? You have to see like which one is positive, which one is negative actually, right, teacher?
Negative
But
sign
then
must
B
be
since
there.
don't have charge
Negative sign must be there. If a negative charge,
and it's
negative
positive
sign,
sign also.
then you just add them up.
Like, so negative 360 plus 750.
Yeah, that's all.
Ooh. Okay.
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 You can see very simple calculation only, and a lot of maths, that's all. But you should also know how to calculate the resultant field, which I haven't
Oh, I
done
thought
it.
it'd be complex.
That one be complex, you can try that out. Electric field line and equal potential surface of a point charge. That is a point charge. Positive point charge plus Q. Right? They are just using this formula, that's all. So electric field is outside, all following the radius. That's the electric field, E vector. So all points on the equal potential surface, that's what it means by equal potential, have the same potential. All points at the same distance from the charge has the same potential. We look at this equation. Right? R the same, V is the same. So we can expect concentric sphere, and they are not evenly spaced because it's not a uniform field. Yeah, it becomes stronger at the center and becomes weaker and weaker further away. The value is not evenly spaced. These are concentric sphere, right? Nearer becomes smaller, further and further become far apart, showing that it's not uniform. Right? The charge is at the center of the sphere. Right? They are all concentric sphere, radius r. So when we move on the surface of this particular sphere, no work is done. Right? Because they're equal potential surface. Potential is the same, no different in potential. And then from this formula, we just take it up. Right? So we can see that for all this line, if our Q is constant, our 4 pi epsilon naught is constant, then our V times R is constant. Right? This is inversely proportional. V and R are inversely proportional. So if it's a parallel conducting plate, page 19, number 5 in your book, then the line, the electric field are vertically downwards parallel, equal distance away. The potential surface also evenly spaced.
Parallel.
And parallel, correct. Right, that's for parallel conducting plate. Uniform field.
Did you go to the previous slide one?
Previous slide is for point charge.
No, I just want to see back again, teacher. Want to ask
Point
it
charge.
one shot. No work is done on a charge. Oh, correct, teacher. That means it's there only, what, teacher? It won't do anything, right? because it's always in the sphere, it cannot do anything, right? Actually,
As long as it's on the sphere, it's an equal potential
no work
surface.
done. Okay, next slide then, teacher.
Whereas for uniform field, as long as it's on any of these straight line, there's no work done. Okay. Equal potential surfaces are parallel and evenly spaced. Electric field lines point towards a lower potential. Right? This is lower potential, defined from a positive to negative, so high potential to low potential. Right? And in this case, our potential difference divided by a change in delta x is a constant. That means if we take that potential difference, right, 10 minus a divided by that distance, same with the others, is a constant. Okay, try this one. Yep, what's the electric field strength?
Yeah, just a second, electric field strength, there's a formula for this, right?
V over D.
Oh, I thought Q over 4 pi epsilon r
No,
square.
no, that is for a point charge. This is just the potential difference across the plate divided by the separation of the plate.
Oh, that means we use that formula for when, actually?
What formula?
I mean, for the A one, that formula,
Don't know what you're talking about.
No, you say like don't use that other one. You say use this one.
You
like,
must know what
how
is.
to
You must know if it's a point charge. A point charge is this formula. Must
point
memorize.
charge. Okay.
And then if it's a uniform field, is this formula. Potential difference divided by the distance, by the separation. That's all. So then we are just using this formula, that's all. This is a uniform field. Yeah.
Give me a minute, sir. Distance are from what's that? They say electric field strength between the plates. So 400 divided with 4 pi epsilon. Radius is what?
Hey, got a radius here.
No, the
Yeah, just
2.0
using this
cm.
formula. Just using this formula. Potential difference
The
divided by the separation.
but then the 2.0 cm there.
That is the separation, not the radius. Must read carefully.
Okay. Oh, D and R completely different. Okay.
So I essentially have to find the potential difference first. Then use the formula.
Oh, that's it.
That's all.
Oh.
Okay.
Okay.
Then what's the electric field strength? 0.1 surface below the upper plate. Yep. We have to change in 10 minutes time. Yep.
They say below the upper Plate.
Upper plate is 400 volt. Upper plate is 400 volt. So 1 cm below, the separation is 2
So
cm.
400 divide 0.1 lah. No, 400 divide with 0.001.
No,
Yeah.
it's a uniform field. It's trying to trick you. That's why see whether you study or not. It's the same value. It's a uniform field.
What?
It's a uniform field. At any
Then
point,
how
the E
you?
value is the same. Doesn't matter about the distance.
Oh, it's a trick.
That's what it means by uniform field. Okay, what's the force on the electron?
The forces.
You have done your homework, you should be able to remember the force formula.
Oh, force formula. This one got two forces here. So 400 times 400 divide with 4 pi epsilon.
Where got 4 pi
And then
epsilon? The force is just basically E times your Q, that's all.
EQ.
Your Q is your charge on the electron. Yeah, what's the problem?
Just a minute, je. Okay, so the 40 times with Q. What's the Q?
You have
Q
to
is
look
the
at
electron, right?
you have to look at your constant, physical constant data sheet.
Q is a constant, right?
Yeah, you must know where to find the constant on your data sheet.
Oh. Okay, so 1.6 times 10 to the power 19 times 4 times 10 to the power of 4.
Yeah,
So the answer you get is 6.4 times 10 to the power of negative 15.
yeah. So you compare
Yeah,
with the weight of the electron, you can see the weight of electron is much too small. Right? That's why we won't bother about the weight when we do the calculation. Gravitational force is negligible compared to electric force.
so the W equals to mg is negligible lah.
Yeah, we don't bother usually when we do calculation. Unless it's an oil drop.
Okay.
Okay, what's the acceleration? Oh, this is know how to calculate.
We found the force already, right, teacher,
Yeah,
just now.
yeah. This is
And
your
then
last
we know,
semester's work.
F equals to QE just now. So now F equals to MA lah.
That's all.
Wait, force is 6.4 times 10 to the power negative 15. Mass, go to the previous page again. Did we know the mass? The mass.
Mass, you can go to your constant table, data sheet to get the mass. You must know where to find it. Right, make sure you photostat a copy. Then you can use it every week. Know where to find it in your exam.
You can send me. Oh, you mean from that past year book?
I've given you last semester already. It's the same data sheet. Values of physical constant.
You did give it. Yep.
Just photostat it. So that I know where to find it in the exam.
What the M value answer?
Mass of electron is 9.11 times 10 to the power minus 31. Yeah, that's the mass of the electron.
Oh, okay. So A means it will be FOM, so 6.4 times 10 to the power negative 15 divided with 9.11 times 10 to the power negative 31. Yeah. I get MS negative 2. And E, the speed of electron reaching the upper plate.
Yeah, what you studied in last semester can be used also. Motion,
You mean the V square, that one or
equation.
larger?
Yeah, all these formula you are required to remember and know how to use it.
Okay. We
know
do
the
have the acceleration.
We know the speed.
Well,
We know the distance.
okay, yeah, distance we know. So S and A we know. I mean we know V is unknown. So the other one U lah, U is 0, right?
Yeah, it's at rest initially.
So V square equals to U square plus 2AS lah.
Yeah, put in your value and calculate out.
That's it. Yep. Oh, so this one they purposely will do like from last semester one lah.
Yeah, you are required to
You have
know.
to remember.
Then calculate the work done
Okay.
on the electron. Yeah, two formula. Either formula can use 4 times
Okay.
distance or V times Q.
Or 1/2 fx square.
1/2 fx square. Where do you get this formula?
The work done. Sorry, that one different one. That one kx square. Silap already.
F times x or VQ. Potential times your charge.
So we know the force, we know distance, so can times already lah. Yeah, okay.
Okay, 5 minutes break. While I change the new
Okay.
Zoom.
Okay, can, Thank you.